Hi everybody, welcome to Nursery Production and Management. Our video lesson today will be fertilizers. And we'll start out by taking a look at some of the different types of fertilizers that are used in the nursery industry. These are the four basic types of fertilizers: quick release fertilizers, slow release fertilizers, controlled release fertilizers, and water soluble fertilizers. Quick release fertilizers. These fertilizers immediately dissociate into their constituent ions when they dissolve in the soil solution. For example, ammonium nitrate dissociates into the ammonium ion, NH4+, and the nitrate ion, NO3-. These ions are immediately available to the roots of plants for absorption. Let me go ahead and draw a molecule of ammonium nitrate for you. So it'd be NH4 and O3. So that is ammonium nitrate. So when this comes into contact with the soil solution or water in the soil, this molecule is going to dissociate into its constituent ions. So one ion that's going to break off is going to be the ammonium ion. That's the NH4 plus ion. And then the other ion is going to be the nitrate ion, which is indicated by NO3 minus. So these two ions would exist in the soil solution, and they would be easily available for the roots of plants to absorb and use as a source of nitrogen. So that's a good example of a quick release fertilizer. Slow release fertilizers have a slower release rate than quick release fertilizers. The rate and duration of release are not controlled because they depend upon microbial organisms whose effectiveness is dependent upon soil temperature and moisture conditions. Examples of slow release fertilizers include nitroform, which would be an example of a synthetic slow release fertilizer, and natural organic slow release fertilizers such as green manures, animal manures, and compost. So what we are saying is that this is a class of fertilizers that requires some microbial decomposition in the soil in order for the nutrients to become available to plants. So the nutrients are not going to be available to plants immediately like they would be in the quick release fertilizers, but they become available slowly to the plants as microbial activity starts to break these compounds down. The third group or type of fertilizer is called the controlled release fertilizer. Controlled release fertilizers have become the industry standard. They are encapsulated with materials that control the rate and duration of nutrient release. However, the rate of release is not dependent upon soil microorganisms like the slow release fertilizers are. Factors controlling the release of controlled release fertilizers are the availability of water and the soil or medium temperature. The image on this slide shows a handful of Osmocote controlled release fertilizer granules, or some people refer to these as being prills. This slide is showing us how controlled release fertilizers actually work. So if we begin on the left-hand side of the diagram, I'll just go ahead and write the number 1 here. Every granule is covered by an organic coating that regulates the daily release of nutrients. Granules contain different fertilizers depending upon the analysis of the fertilizer. So inside each granule or prill, you may have nitrogen, phosphorus, potassium, magnesium, boron, copper, and so on. Step number 3, water penetrates through the coating and dissolves the nutrients that are inside the granule or prill. The dissolved nutrients are released from the granule or prill through the coating by osmotic pressure. Influenced by the temperature, the nutrients are released at a constant, regular, and controlled rate during the longevity of the fertilizer. Longevity refers to how long the fertilizer lasts, and it is going to be dependent upon the temperature of the soil or the medium that the plant is growing in. The warmer the temperature of the soil or medium, the shorter the longevity of the fertilizer will be. And the last type of fertilizer that we want to look at are the water-soluble fertilizers. These are granular or powdered formulations that are easily dissolved in warm water to form a concentrated stock solution. The stock solution is subsequently injected into the nursery or greenhouse's water system. Fertilizing and irrigating crops in this manner is called fertigation. Let me go ahead and write that word on the slide. Fertigation is the process of irrigating and fertilizing at the same time, and this can be accomplished using water-soluble fertilizers and a fertilizer injector. This slide shows an example of a mobile fertilizer injector. The white 5-gallon bucket holds the concentrated stock solution. The dilution ratio is adjustable, meaning that the amount of fertilizer being injected can be changed as needed to accommodate the differing fertility requirements of your crop. Fertilizer analysis. The analysis of a fertilizer will be written on the bag or package. It tells you what nutrients are inside the bag. The 3 numbers that make up the analysis of this fertilizer, 19, 6, 12, tell us that the fertilizer contains 19% nitrogen, 6% phosphate, and 12% potash by weight. The first number in the analysis, 19, indicates the percentage of nitrogen in this particular fertilizer. The next 2 numbers identify the percentages of phosphate and potash in the fertilizer. These 2 nutrients need to be corrected using conversion factors to convert their values into percent phosphorus and percent potassium. So let's take a look in the next slide how we do that. To convert percent phosphate to percent phosphorus, multiply by the conversion factor of 0.44. So if we take the 6% phosphate that was in the analysis of the fertilizer, multiply that by the conversion factor 0.44, then we can determine that 2.64% of this fertilizer is actually elemental phosphorus, P. And we can do the same with potash. We can convert percent potash to percent potassium by using the conversion factor 0.83. So I know by looking at my analysis that the fertilizer was 12% or contained 12% potash. If I multiply that by 0.83, I can determine that the fertilizer contains 9.96% of elemental potassium. If you wanted, you could rewrite the analysis of this 9,6,12 fertilizer as follows. And let me go ahead and do it. So I could write it like this: 19-2.64 This rewritten analysis tells you precisely the percentages of nitrogen, phosphorus, and potassium that are found in this particular fertilizer. Let's talk a little bit about how fertilizers are applied, and we'll begin by looking at the application of fertilizers to field-grown nursery stock. And we'll start with trees. A general recommendation for trees is to apply 75 pounds of actual nitrogen per acre to establish shade trees twice a year. Two good times to do that in the south would be February, just as the trees are beginning to start their new growth in the spring, and then again in June. So if you add 75 pounds of actual nitrogen per acre in February plus another 75 pounds of actual nitrogen per acre in June, this represents a total of 150 pounds of actual nitrogen per acre per year that would be applied to trees growing in a field situation. For shrubs, the recommendation is no more than 50 pounds of actual nitrogen per acre at each application. And again, the application could be split in a similar manner to the way we split the application for trees. One application occurring in February and the second application occurring in June. That would mean that no more than 100 pounds of actual nitrogen per acre per year should be applied to shrubs growing in the field. A broadcast spreader spreads fertilizer indiscriminately across a wide swath. A broadcast spreader would fertilize both the ornamental plants growing in the rows and the grass strips between the rows. Because this spreader has been modified with a banding attachment, the operator is able to band the fertilizer on both sides of the ornamental plants without applying fertilizer to the grass strips. So using a banding attachment can help your fertilizer application be more precise, and it can help you put the fertilizer where it's actually needed, which is right alongside the rows of ornamental plants without wasting fertilizer on the grass strips. Of course, there's always going to be some math involved in fertilizer calculations. Remember that a 20-10-10 fertilizer, for example, contains only 20% actual nitrogen on a weight basis. There is a useful formula that we can use for determining how many pounds of fertilizer to apply. And here's the formula. So the pounds of fertilizer, which are over here on the left, is going to be equal to the application rate of the nutrient in pounds, right here, divided by the percentage of that nutrient in the analysis. So that is the standard formula that you would use to determine how many pounds of fertilizer you should apply. Let's go ahead and run through an example. This example is an example of applying fertilizer to trees that are growing out in the field. You want to apply nitrogen at a rate of 100 pounds of nitrogen per acre. How many pounds of a 20-10-10 fertilizer should be applied in a split February-June application to 10 acres of nursery stock? Using the formula that I just provided you in the previous slide, you can calculate how many pounds of fertilizer you would need. Pounds of fertilizer is equal to 100. So 100 is the application rate. So where did I find that? Well, in this problem, it's right up here. I say that the rate of application that we want is 100 pounds of nitrogen per acre. So that is the rate. So I took the 100 and I just plugged it in right there. And then the other piece of information you need is you need to know the percentage of nitrogen that's in the analysis. Well, here's the analysis, 20-10-10. And we know that when you look at an analysis, the very first number in that analysis tells you the percentage of nitrogen in that particular fertilizer, which in this case happens to be 20%. So I'm taking the 20% and I'm sliding it down here. Now the only thing I'm doing is I'm converting 20% into decimal form, so it'd be 0.20. So now I have 100 divided by 0.20, and that comes out to be 500 pounds of fertilizer. Okay, now that would be 500 pounds of fertilizer that you would apply to 1 acre over the course of 2 applications. Okay, and the reason it's such a high number is because you have to remember that the fertilizer that we're using is not 100% nitrogen. There's only 20% nitrogen in that bag of fertilizer, so we have to kind of bump our rate up considerably in order to compensate for the fact that that bag does not contain 100% nitrogen. All right, and then carrying the problem through, we know that we have 10 acres of nursery stock that we need to treat. So on this line, we're simply multiplying 500 pounds per acre times 10 acres. That would give you a total of 5,000 pounds of fertilizer that would need to be applied in 2 applications to 10 acres of nursery stock. But remember, the problem is asking us to split this up over those 2 applications. So let's go ahead and do that. So if I take 5,000 pounds and divide it by 2, that means I would be applying 2,500 pounds of fertilizer in each application. So the first one would be occurring in February, and then I would also apply another 2,500 pounds of fertilizer in June. And remember, this is over 10 acres now, not over 1 acre. So that's, I think, a nice example of how that formula can help you solve fertilizer math problems. Let's talk about the application of fertilizers to nursery stock that is growing in containers. This slide identifies 3 different methods of applying fertilizer to crops that are growing in containers. And those 3 methods are top dressing, dibbling, and incorporation, which is the nursery standard right now. In top dressing, shown on the left, and that is this diagram right here, this is top dressing. All of the fertilizer is placed on the surface of the growing medium. So that's what these blue granules are supposed to represent. They represent the fertilizer. So in top dressing, all of the fertilizer is placed on the surface of the growing medium. There are some potential problems with this application method. Firstly, if the pot were to blow over, the plant would lose some or all of its fertilizer. And secondly, this type of application method seems to favor weed growth. Dibbling is illustrated in the center. Let me go ahead and do some erasing here so we can clean this up. All right, so dibbling is shown in this picture. We'll just abbreviate that as DB. In this method of fertilizer application, the fertilizer is placed into the planting hole during pot filling, and then the liner is planted on top of the fertilizer. So here is the fertilizer, and then this is the liner. So during the process of potting up a liner, a planting hole has to be created, then the dibbled amount of fertilizer needs to be added to that hole, and then the liner gets planted on top of the fertilizer. All right, let's go ahead and erase that. And then finally, the third method of applying the fertilizer is incorporation. We'll just abbreviate that INC. That means incorporation. And that is the process of blending the fertilizer into the medium before the liners are potted. Now there's one thing to keep in mind, and that is if you have a crop that's going to stay in its container for several years, you will need subsequent top dressing or fertigation to maintain fertility levels. So what I mean by that is, let's use this as an example. So I incorporated fertilizer into the medium, and then I'm going to take this container after it's potted up, and I'm going to set it out with hundreds of other containers out in a block of container nursery stock. So there's the containers, and then of course you have the plants growing in the containers, and then you have the incorporated fertilizer that was incorporated or mixed into the growing medium. Well, let's say, for example, that this particular crop is going to stay in this same container for 2 years. Well, it looks like I have the first year covered because I incorporated fertilizer, but what's going to happen is over the course of the growing season, the plants are going to use that fertilizer, and some of that fertilizer is going to be leached through the container medium and lost. So when I start my second growing season, these plants are going to be deprived of fertilizer. So I'm going to have to come up with some way to provide them with the nutrition they need to grow during that second growing season. One way that I could do that is at the beginning of the second year, before the plants start actively growing, I could top dress the containers with additional fertilizer, or I could fertigate. If I was set up to do that, I could supply fertilizer to the plants in that fashion. So that's always something to keep in mind, is that when you dibble or incorporate, If the plants are going to remain in the containers for several years, you need a strategy for providing nutrition to those plants in the second or third years after they were potted up. This slide shows a batch mixer, which would be suitable for incorporating fertilizer into a potting medium, and this batch mixer would also work for mixing different media ingredients together to form a potting medium in the first place. Batch mixers come in different sizes based upon their volume in cubic yards. If you know the volume of a batch mixer, or if you know the volume of the potting medium that you're going to add to the batch mixer, it's pretty easy to calculate how much fertilizer to add for incorporation. Let's take a look at this problem. So we have a batch mixer that has a capacity of 6 cubic yards, and we look on the label for Osmocote 2449, and we determine that we want to use the low rate of incorporation, which turns out to be 11 pounds of fertilizer per cubic yard of medium. So how many pounds of fertilizer should be added to this particular batch mixer? And the answer would be 66 pounds, because it has a capacity of 6 cubic yards times 11 pounds of fertilizer per cubic yard would give you a total of 66 pounds of fertilizer that would need to be added to this batch mixer. Now, this is providing that the batch mixer is filled to its full 6 cubic yard capacity. If you're mixing less than 6 cubic yards, then obviously you would need to adjust the rate. Let's take a look at the application of water-soluble fertilizers. Recommended rates for water-soluble fertilizers are expressed in parts per million of nitrogen typically. Parts per million is a measure of concentration. The higher the parts per million, the higher the concentration. To get a better feel for what parts per million actually is, let's run through a simple example using red dye, and you could kind of think of the red dye as just being red food coloring. So what is the concentration, or what would be the concentration in parts per million of 1 fluid ounce of red dye added to 10 gallons of water? To do this kind of problem, we need to have the same units on the top and bottom. So I can either convert ounces of red dye to gallons of red dye, or I can convert gallons of water to ounces of water. I choose to convert gallons of water to ounces. Ten gallons of water is 1,280 fluid ounces. The next step in solving this problem is to set up something called a proportion. I'm adding 1 fluid ounce of dye to 10 gallons of water. Now, I just told you that I converted the 10 gallons to fluid ounces. So really what I'm doing is adding 1 fluid ounce of dye, that's right here, to 1,280 fluid ounces of water, which is the 10 gallons of water. So the way I set up the proportion is I go 1 is to 1,280 as X is to a million. Now, the reason I put million in the denominator here is because I want an answer that's going to be parts per million. So that's why I used 1 million in the denominator. So let's go ahead and solve this proportion. Cross multiply and solve for x. So if I cross multiply, I have 1,280x is equal to 1 million. And then if I solve this equation for x, x would be equal to 1,000,000 divided by 1,280. So the concentration of 1 ounce of red dye or food coloring mixed into 10 gallons of water is about 781 parts per million. Hopefully that will give you maybe a slightly better understanding of how parts per million works. Remember, it's a way of measuring the concentration of something, and it's used a lot in the greenhouse and container nursery industry, especially when we're using liquid fertilizers that are being passed through an injector. So it's very, very common to run into the term parts per million in those applications. Okay, this shows how a typical fertilizer injector would be set up in a greenhouse or in a container nursery. And let me just run through some of the things that you would expect to find in this system. And I'm going to circle these things as I talk about them. And I'm going to use the color white to circle them. So first off, you have a filter that's right here. When you're using any kind of drip irrigation, it's always important to have a filter built into the system to capture any particulate matter that might plug up your emitters. You don't want your emitters becoming clogged because it's a nuisance, and that means that maybe that pot is not going to be getting the amount of water that it should. So you always need to have a filter. The second part of this system that I want to illustrate are something called solenoid valves, and in this diagram there's several of them. There's one here, one here, one here, and one here. Solenoid valves are electric valves that are wired to some kind of a control panel so that you can regulate when they're turned on and turned off. All right, the next part of this system is a check valve that's right here. That just ensures that water cannot flow backwards through the system. This is the injector, and right here is where you would adjust the ratio, the dilution ratio, to either increase it or decrease it, depending upon how much fertilizer you want to inject into your system, into your line. Down here is the stock tank, which would contain your concentrated fertilizer stock solution. These are bypass valves. So these let you either inject fertilizer into your water or bypass the fertilizer injector and just irrigate with clear water that doesn't have any fertilizer in it. And then finally, when you get out to the actual lines that are going out to the crop, this is called a pressure compensating regulator. Here's another one right here. So this is on each drip line. And this basically adjusts the pressure of the water so that it's optimized for whatever drip line you're using. And then finally, these would be the drip lines that would be going out to water your container crop. That was just kind of a brief look at some of the different parts you would expect to see in an irrigation system that's using a fertilizer injection system. I mentioned the dilution ratio before, but the amount of concentrated fertilizer that's injected into the water line can be changed by changing the dilution ratio. Commonly used ratios are 1 to 100, 1 to 128, and 1 to 200. For example, an injector set at 1 to 100 will inject 1 gallon of fertilizer concentrate for every 99 gallons of water that flow through the injector. Now keep in mind it's not doing it quite literally like this. So in other words, it's not going to let 99 gallons of water go through and then all of a sudden magically inject 1 gallon of fertilizer into your line. It's going to do this incrementally as water passes through the injector. So it's going to be lots of small little doses of fertilizer that are getting injected into your water line. In fertilizer math problems, your job is to calculate how many pounds of fertilizer to add to your stock tank. The stock tank, as I mentioned before, is the container that's used to hold or store your concentrated stock solution of fertilizer. And there are 4 variables that we need to manipulate when trying to solve problems using water-soluble fertilizers and injectors. One variable is we have to know the desired rate of fertilizer application, and that's usually going to be expressed in parts per million. And normally that's going to be for nitrogen. So typically um, a typical rate might be 150 parts per million of nitrogen or 200 parts per million of nitrogen. The second variable that we need to know is going to be the percentage of fertilizer of that particular fertilizer element as noted in the analysis. If we're talking about nitrogen, if we're using a rate and we're saying 150 parts per million nitrogen, then we need to know how much nitrogen is in the fertilizer that we're using. And we're going to get that information from the analysis. The third variable is the dilution ratio of the injector, and we have control over that most of the time because we can change that. However, there are some injectors that have a fixed dilution ratio, so you should be aware of that. And then the last variable is the volume of the stock tank in gallons. To make life easier for us, there are tables, and many of these tables are available on the internet. Some of these tables might actually be published right on the bag of fertilizer for you to look at. The tables make the job of manipulating or organizing these 4 variables much, much easier. So let's go ahead and take a look at an example. This is an example of the kind of table I was talking about previously. So let me go ahead and orient you to this particular table. The table is divided into 3 major sections depending upon the percentage of nitrogen in the analysis of the fertilizer you're using. For example, if you're using a 30% nitrogen formulation, then you would be up here at the top. If you were using a 25% nitrogen formulation, you'd be in the middle. And then if you were using a 20% nitrogen formulation, you would be down here at the bottom. So these, where do you find these numbers? Well, the 30, the 25, the 20, they would be the first number in the analysis of the fertilizer that you're using. 3 major sections. Then within each section, you can see that there are different dilution ratios. Let's take a look at the top. So the dilution ratios, your options are 1 to 15, all the way to 1 to 200. The next part of the table deals with your desired rate of application for that particular nutrient that you're concerned about, which in this case is nitrogen. So there are 3 options. There's a rate of 100 parts per million nitrogen, 150 parts per million of nitrogen, or 200 parts per million of nitrogen. Okay, this tells you per gallon of concentrate up here at the top. Let's go ahead and put this table into action by doing an example. A grower is using a 30-10-10 fertilizer and wants to apply 150 parts per million of nitrogen at a 1 to 128 injection or dilution ratio. How many pounds of fertilizer should be added to make 100 gallons of stock solution? Let's go ahead and use the table to solve this problem. So from the start, I'm going to try to erase some things to get rid of some of these lines here so it's a little easier to see. Bear with me. That's better. If we go to the original question, we can see by looking at the analysis of the fertilizer that the fertilizer is a 30-10-10 fertilizer. So that means that this particular fertilizer contains 30% nitrogen by weight, which means that we're going to be using the top or upper part of this table. The question tells you that we're going to be using a 1 to 128 dilution ratio, so that means our answer is going to be somewhere along this line. The question is telling you that we want to apply the nitrogen at 150 parts per million. So going across the top, these are our rates, and the rates for 150 parts per million, that's going to be right here. So we're going to be looking at this column of numbers. Okay, so looking at it, I can see right here that where these 2 lines intersect, 8.64 ounces. So these are dry ounces, not fluid ounces. So this is saying that you would need to add 8.64 ounces of fertilizer per every gallon of concentrate that you want to make. Well, from the question, we can determine that we want to make 100 gallons of stock solution. So we simply take 8.4 ounces, that's how much we need for each gallon, and then we are going to multiply that by 100. So that would be 864 ounces. That's kind of an awkward number, so I'm going to convert that back into pounds by dividing by 16, and that comes out to be 54 pounds. So the bottom line is, to do what you want to do in this question, you would need to add 54 pounds of this 30-10-10 fertilizer to 100 gallons. and typically the fertilizer dissolves better in warm water. So practically speaking, how you would do this is if I draw you a little stock container here, I would go ahead and put in some water, maybe 20 gallons of water or so. And then I would start adding my fertilizer. And this needs to be agitated, so it should be constantly mixed. And then after I got all my fertilizer in, which would be 54 pounds, then I would continue to add water until I got to the 100-gallon mark, which presumably would be somewhere up near the top. All right, then I would have 100 gallons of concentrated stock solution. And when I inject that at the 1 to 128 dilution ratio, coming out of the end of the hose is going to be 150 parts per million of nitrogen, which is the desired rate that I said I wanted in the question. So the tables make life much easier. There are ways to calculate this without the tables, but the tables are ubiquitous. They're all over the internet, and they're probably going to be published right on your bag of fertilizer. So that's going to help you. But I think you need to understand that the table is kind of juggling those four variables that we just discussed earlier. If you have a crop of plants either in a greenhouse or a crop of container plants in a nursery setting, you are going to need to monitor or keep an eye on those plants to make sure that you're not over fertilizing or under fertilizing them. And the way that you can monitor your plants is by measuring something called electrical conductivity. And you can also measure a pH because typically the meters or instruments that you purchase to measure EC will also measure pH at the same time. But let's focus for a minute on electrical conductivity. Electrical conductivity is a measurement of the concentration of soluble salts in a solution. Higher concentrations of soluble salts result in higher electrical conductivity readings. Fertilizers of any type eventually become soluble salts in the container medium. Monitoring electrical conductivity is a standard practice in container or nursery management. It gives a grower a tool that can be used to monitor the fertility levels in the growing medium of a container crop. It can help a grower decide when to fertilize or warn a grower when fertility levels are becoming toxic and the crop needs to be rinsed with clean, unfertilized water. A meter, like the one pictured in this slide, can measure both electrical conductivity and pH. Knowing medium pH is important because we know that nutrient availability changes with pH. And we know that for plants there's a certain pH sweet spot where we would ideally like to maintain our pH. And typically the range that a lot of horticulture instructors throw out there is somewhere between about 6 and 7. And that's kind of a good range for plants that are, growing outside in the field. But in a container nursery setting or in a greenhouse setting, I think the actual ideal pH would be even a little bit lower than that. The units that are used to measure electrical conductivity are a little bit difficult. They're a little confusing, and different electrical conductivity meters are calibrated to record different units. So let's look at some of the common ways that electrical conductivity is recorded, and I'll circle them as I talk about them. So one way is in decisiemens per meter, that's right here. So a Siemens is the standard unit of electrical conductance. A second way that electrical conductivity can be recorded is in millimos per centimeter. And then finally, the third way is in microsiemens per centimeter. As it turns out, 1 decicentimeter per meter is equal to 1 millimos per centimeter, which is equal to 1,000 microsiemens per centimeter. Wow. So try wrapping your head around that. But I think it's important that you understand that different meters are calibrated to record in different units, and you need to understand which units your meter, your instrument is using, and that there is a way to convert from one type of unit to a different type of unit. And this little formula right here can help you do that. In the full PowerPoint version, there is a link here to a very nice video that's put out by the University of Kentucky, and it talks about the pour-through method to monitor electrical conductivity, and it's definitely worth your time to take a look at this video. I'm going to summarize the steps verbally so you can listen to the steps, and then hopefully when you get a chance, watch the video to kind of reinforce the steps that I'm going through. So the procedure goes as follows. So number one, the first thing you would do would be irrigate your container nursery stock. And when we say irrigate, we're meaning irrigating with clear, unfertilized water. Then we're going to allow the containers that were just irrigated to drain for approximately 30 minutes. After the containers have drained, we are going to go out into the block of containers, and we are going to randomly select certain containers that we are going to measure. We are going to place leachate collection pans under the randomly selected pots in the block of container nursery stock. So what is a leachate collection pan? It's basically a pan, a shallow pan. It could be made out of plastic or aluminum foil. It's going to be maybe 3 or 4 inches deep, and it's going to be large enough in diameter, to fit whatever container you're going to place into it. So we are going to randomly select pots and then place them into or onto these leachate collection pans. Then we are going to take some additional irrigation water. We're not going to turn on the irrigation system, but we're going to go out to these containers, maybe with a bucket or some way of applying additional irrigation water to the pots that we are choosing to sample. And we are going to add enough irrigation water to cause a measurable amount of leachate to drain into the collection pan that the pot is now sitting in. We are going to measure the electrical conductivity of the leachate that we collect in the pan. And we are going to subtract from that measurement what's called the background electrical conductivity of the irrigation water. So keep in mind that even water from your tap at home has a measurable electrical conductivity. As growers, we are interested in the fertility levels of the medium inside the containers. This is why we subtract the background electrical conductivity of the irrigation water from the electrical conductivity of the leachate that was collected. And then finally, the last step is we are going to record the sample's corrected electrical conductivity and its pH. And then over time, we are going to keep track of that data. Why do we do that? We do that because when monitoring electrical conductivity levels, if we find out that the levels are too high, then basically we have a couple of choices, a couple of management options. One option is we can water the crop with clear irrigation water to leach out the excess fertilizer. Another management option is that we can decrease the fertilization rate. If it turns out the electrical conductivity is too low, then our management option is to fertilize. We want to add fertilizer to get that electrical conductivity up into the optimum range for whatever crop we're growing. Now in the video, they briefly describe what some of those optimum ranges are. On the internet, you can find all kinds of information specific to different crops at about what levels electrical conductivity should be maintained at throughout the production cycle of an ornamental plant growing in a container. Well, I hope you enjoyed that as much as I did explaining it to you. That's all for now. Thank you so much for watching, and we will see you next time.